All right, so this is Unit 1, Lesson 2, the fundamental counting principle. All right, so before we get into what the fundamental counting principle is, we have some definitions at the top of our notes, some things that we need to define now because we will be using them quite frequently throughout the rest of the unit. These terms are going to pop up a lot. So, following along in our notes here, we have mutually exclusive events. Now we defined this in lesson 1 already, but let's go ahead and write it here again. So mutually exclusive events, uh, these are events that cannot happen at the same time. So events that cannot happen at the same time. And remember, think of like flipping a coin, right? I cannot flip a coin and get heads and tails. That would be impossible unless I flipped two different coins or I flipped the coin twice. But I can't possibly get both in one flip. Rolling a die, that was the other one we talked about. You can't roll a die and get a 5 and a 6. That's impossible. Okay, cool. We also have these two new terms here. We have independent events and we have dependent events. They are exactly as they sound. So independent events, these are events that do not affect the probability of each other. All right, so in this one, you've got two things that are occurring, and one has no impact on the other. So events that do not affect the probability of each other. Okay, here's an example of this one. So let's say you get up in the morning and you're afraid you're going to be late to school. Okay, cool. Well, the probability of you being late to school has nothing to do with the probability of you choosing a red shirt in the morning. The color of your shirt does not affect whether or not you're late. Hopefully, if you're running late, you're just grabbing whatever you've got and you're throwing it on and you're out the door. But whatever you choose to wear that day has no effect on whether or not you arrive to school on time. So those would be events that do not affect the probability of each other. Okay, dependent events. This is the exact opposite, right? So we would say for dependent events, one event affects the probability of another event. So let's talk about that same example. You're afraid you're going to be late to school. All right, well, hold on, let me finish the definition here. Okay, so you're afraid you're going to be late to school. Well, the probability that you're late to school is directly affected by the probability that you woke up on time, right? So if you got out of bed late, well, you're probably going to be late to school. Those two are dependent events. The probability of one happening is definitely going to impact the probability of another happening, okay? So the percent chance that you woke up late, that's going to affect the percent chance that you arrived to school on time. Okay, now, these types of events are going to pop up a lot throughout our study of statistics, but let's get into what the fundamental counting principle is. So, fundamental counting principle, right here, definition. It says a mathematical rule that calculates the total number of possible outcomes in a situation. It is sometimes called the multiplication rule. All right, and then right here in the highlighted portion, it says if there are n ways to do one thing and m ways to do another thing, then the total number of outcomes is equal to n times m. Great. That's fancy math speak for, let's look at this example here. How many possible outcomes are there when you roll two fair dice? Okay, now remember, I'm rolling two now, okay? So on the first die, I have a 1 through 6, right? I could get a 1, a 2, a 3, a 4, a 5, or a 6. There are 6 outcomes. On the second die, there are also 6 outcomes. So in total, there must be 6 times 6 possible outcomes. So according to the fundamental counting principle, there are 36 possible outcomes. Okay, now, what I want you to be careful of here, all right, is yes, you could get a 1, and let's say you could get a 5, all right? This is not the same as a 5 and a 1. Okay, and you might be thinking, now wait a minute, either way, if I'm playing a game, for example, and I roll 2 die and I get a 1 and a 5 or a 5 and a 1, either way I got a 6. You're right. However, these are two different possible outcomes, okay? In one of them, the 1 was on the first die and the 5 was on the second die. In the other one, the 5 was on the first die and the 1 was on the second die. Those count as two different things because they're both possibilities. So we're not talking about possible rolls here. We're talking about possible outcomes total. Okay, great. So let's move on. Here we go. It says you can use the multiplication rule, so the rule we just did, 6 times 6 gives us 36, to find the number of outcomes of a situation, or you can draw a tree diagram to help you visualize how many outcomes there are. Now, the problem with tree diagrams is you saw in the last lesson that sometimes, especially if they have a lot of branches, tree diagrams get really crazy and they take too long to draw. That is why the multiplication rule comes in handy, okay? So right here, for this example, right here at the bottom of our first page of notes, I'm actually going to show you both ways, all right? So over here, I'll draw a tree diagram. Okay, and over here, we'll do the fundamental counting principle. So fundamental counting. Remember, this is sometimes just called the multiplication rule. Okay, so it says you visit the coffee cart during the day to get a muffin and a sports drink. The choices of muffins are chocolate, blueberry, or banana nut. The sports drinks are either fruit punch or blue cherry. How many possible combinations can you make with these choices? All right, well, the fundamental counting principle, all right, that's what we're learning now. Let's think about a tree diagram since you guys already know those. You could start at the coffee cart and you could get either a chocolate muffin, a blueberry muffin, or a banana nut muffin, right? And then from each of those points, you could get two different sports drinks. So from here, let's go ahead and label these. So I'll do C for chocolate, I'll do BL for blueberry, and B for banana, or BN for banana nut. Okay, great. Then from those choices, I have two kinds of sports drinks for each one. Okay, so if I'm labeling those, I've got fruit punch, FP, or sorry, not FB, boop, FP, there we go, or blue cherry. Fruit punch, or blue cherry. Fruit punch, or blue cherry. And there are a total of looks like 1, 2, 3, 4, 5, 6 possible outcomes. Okay, so that's how a tree diagram would work. But like I said, especially if there were, imagine there were even more choices of muffin or even more choices of drink, you're going to be drawing a lot of branches, and sometimes tree diagrams just take too long. So that's why the fundamental counting principle comes in handy. If you have a highlighter on you, I highly recommend you use it. Okay. Looks like we have 3 choices of muffin. So there's 3 choices there. And it looks like we have 2 choices of sports drink. And so the fundamental counting principle says, well, there must be 3 times 2 or 6 possible outcomes. Or I guess the word I used in the question was combinations. Okay, very good. Now, for the back page, for these examples, we're just going to focus on using this new thing. We're going to focus on using the fundamental counting principle. All right, so turn it over to the back. It says you are getting ready for school in the morning. You are deciding between 3 of your favorite t-shirts, jeans or sweatpants, and tennis shoes or Nike slides. How many possible outfits do you have to choose from? All right, so once again, it's a good idea to just kind of label what's going on here. So uh, we have 3 different shirts to choose from. Okay, looks like we have 2 different types of pants to choose from. Okay, and it looks like we have 2 different kinds of shoes to choose from. Now, the fundamental counting principle does not stop or it does not limit you to only 2 things. All right, there could be as many choices as you want. So here we have 3 different categories of choices. So all we're going to do is we're going to say 3 times 2 times 2. That is 12 possible outfits. And that's it. Okay, there are 12 possible outfits that we could choose from. Great. Next. Example 2 says your family is going to Best Buy to get a new television. They have LCD, LED, OLED, and QLED screen types. Looks like we have full or widescreen shapes. And then we have 43 inches, 50 inches, 55 inches, 60, 65, and 70-inch screen sizes. How many different TVs is Best Buy offering you? So once again, just figure out how many categories of choices you have and how many choices within each category do you have. So first we have screen types, right? So it looks like we have 1, 2, 3, 4 different screen types. Okay, cool. All right, it looks like we have 1, 2 different screen shapes. Okay, and we have 1, 2, 3, 4, 5, 6 different screen sizes. All right, and once again, fundamental counting principle, all we have to do is multiply all of them together. There are 4 times 2 times 6 possible TVs. So 4 times 2 is 8. 8 times 6 is 48. So 48 different TVs. Nice, lots of choices there. All right, and then last example. It should look really familiar. We're talking about tourists going from Chicago to Miami again, all right? It's pretty much the same problem as last time, except now we're talking about possible outcomes. We're not calculating probabilities, okay? So, just to recap, once again, we have a travel agent. He's planning trips for tourists from Chicago to Miami. He gives them 3 ways to get from one city to the next. And then once they get there, there are 2 ways to get from the airport to the hotel. Or not the airport, from either the airport, the bus stop, or the train station. Great. The cost of each type of transportation is once again given in the table below. And it says how many possible ways are there to travel from Chicago to the hotel in Miami? Okay. So once again, we've got looks like 3 ways to get from one city to the next. And then it says we have 2 ways to get to the hotel. All right. So we have 3 uh, ways to get to Chicago. Or sorry, to Miami. And we have 2 ways to the hotel. All right, so for a total of 3 times 2 equals 6 possible ways. Okay, and then last it says if the tourists were to instead travel to New York City, the subway would be another possible way to get to the hotel. How does this affect the number of possible ways to travel? Okay, so we're still offering airplane, bus, and train. All right, so there are still 3 ways to get to New York. But think about it for a sec. Maybe pause the video, think about it. Uh, should be pretty obvious. There were 2 ways to get to the hotel, but we're saying New York City. Now we have a subway. So we're saying, okay, now there's 3 ways to get to the hotel. Okay. And so, according to our fundamental counting principle, or our multiplication rule, there are now 3 times 3, 9 possible ways to travel. Now, I want you guys to be very careful on questions like this. It did not actually ask us how many possible ways to travel are there between Chicago and New York. It asked us how does this affect the number of possible ways to travel, as in compared to the previous problem. So, if I was really, really going to be careful about answering this question, I would say um, there are 3 more possible ways to travel to the hotel in New York than there are to Miami. Okay, so to Miami, there are 6 possible ways to get all the way to the hotel. In New York, there are 9 possible ways. So if I was really going to answer the question, I would say there are 3 more possible ways to travel to the hotel in New York than to Miami. All right, and that's it for this lesson. This one was a short one. The fundamental counting principle, it's literally just there to save you some time so that you don't always have to draw a tree diagram. However, sometimes tree diagrams give us a visual. So if you're a visual learner, that may be the way to go. If not, this might be the way to go. All right, good job.